Okay, so previous lecture we looked at actuator disk theory, and this was a nice way of using mass and momentum and the Bernoulli equation carefully to look at the performance of propellers and also wind turbines, and look at the way in which the size affects the thrust that they can generate, and to come up with ways to look at the efficiencies of propellers and wind turbines. And this is sort of useful from a sort of a design point of view. So today we're going to look at a subset of the steady flow energy equation. It's called the steady mechanical energy equation. So effectively what this is the steady flow energy equation without the temperature. But what it does do is it includes viscous effects, because this is included in the steady flow energy equation. We didn't neglect it. And we use this equation to look at the pressure drop characteristics of pipe networks. And if you want to put a pump on a pipe network, this equation will tell you what kind of pump that you need, how big it should be, what the losses are going to be, and how you should design your pipe such that you can minimize your pressure drop and choose the smallest pump possible. So, word of warning with this, it's often called the extended Bernoulli equation, but it's not in any form. You can't start from the Bernoulli equation and extend it to get to this equation, and that doesn't stop some textbooks doing precisely that. So very clear sort of guidance from the start of this lecture. You have to start from the steady flow energy equation, simplify it, simplify it, and simplify it, and you can get to the Bernoulli equation. You can't start from the Bernoulli equation and work your way back up, because the whole principle of the Bernoulli equation is that it's inviscid, and if you start making your fluid viscous, then your Bernoulli equation just doesn't apply anymore. Okay, so let's get going and let's try and work out where we go. So let's remind ourselves what the Bernoulli equation does. So it's a energy balance, a mechanical energy balance along a streamline, and we derived this earlier on in an earlier lecture by deriving force balance. So this was the Euler equation, and we derived this, and then we integrated this equation with respect to S, and we ended up with the Bernoulli equation, and we ended up with three energy terms: a kinetic energy term, pressure energy term, and a potential energy term, and the sum of these is always equal to a constant, and this constant is typically called the stagnation pressure, and the stagnation pressure is, if you like, the stored energy in a chamber from which pipe flows come from. Okay, and to remind ourselves what the steady flow energy equation was, it's effectively the first law, a rate of change equation like the first law for energy for this kind of particular control volume, and we have heat transfers across the control volume surface, and we can have work transfers across the control volume surface, and that's this Q minus W term, and then we can have convective transfer of energy due to the flow. So that's what this term was, and if we could assume it's inviscid, we can simplify this and say it's a little bit like this. Okay, so this is what we did when we did the steady flow energy equation, and your steady flow energy equation questions pretty much always assume your fluid is inviscid, and you're using this kind of form for the convective terms, which is much easier than this rather unpleasant integral. So we are going to not make this inviscid assumption. So we're going to work with this particular equation. Okay, and just to remind ourselves, we've got this total energy, and it's the sum of all those components. So it's the three components that we had for the Bernoulli equation: kinetic and pressure and potential, and we've got thermal energy in there as well. So we neglect thermal energy, but we do it in a clever way, and we will come to that in a minute. So we can make some assumptions because we're interested in pipe networks. So let's say we're interested in a pipe, and it might have some bends and some joints and a pump and various things in it. but generally there's one inlet and one outlet. So this is my steady flow energy equation generalized to 1D flow and 2 ports. So this is my energy flowing out of my pipe, and this is my energy flowing in. And we know that the mass flow is the density times the velocity times the integral over the area, generally. Okay, so we're not assuming it's inviscid here. And we know that the inflow and the outflow are the same because due to mass conservation. So we can simplify most of these terms. So let's say we take the integral of P over rho. No, let's not do P over rho. Let's do GZ. So the integral of GZ rho U dA. So we've got to integrate that. Okay, so because the gravity and the Z dimension doesn't depend on the cross-sectional area, we can take this thing out of the integral. So then we have GZ integral of rho U dA, and integral of rho U dA is just the mass flow. So we can write that this term is just the mass flow times GZ. Okay, and we can do the same thing for P over rho, and we can do the same thing for internal energy. Where we get stuck is the kinetic energy term. So we can't simplify this any further because we can't take U squared out because U is going to depend on where we are on the cross-sectional area. So we've got to do something a little bit more clever with these two terms to deal with it in an engineering way. Okay, so if it was uniform, and we'll come on to this tomorrow, next lecture, sorry, no, next slide even, then if it was inviscid, we could just take this straight outside. We wouldn't have to worry about the integrals, and we could do it. But we can't, and we need to account for this viscous velocity profile. Okay, and this is the reason why you can't use the Bernoulli equation, because you just you can't deal with the velocity profile near the wall. Okay, so let's come up with an engineering fix to dealing with this kinetic energy term and making it tractable. So if it was inviscid, like the Bernoulli equation, we could just say that the kinetic energy term is just the mass flow times U squared over 2. And in reality, because we have the no slip boundary, we have a velocity profile that looks like this, and U depends on A, and we can't integrate this. We can't integrate this in a sort of a clever way. So we have to come up with a sort of an engineering fix, and we do that by defining a kinetic energy correction factor. So we call this thing alpha, and what alpha is, it's the kinetic energy in the real case divided by the kinetic energy in the inviscid case. Okay, so this gives us a definition to say, well, the thing that we're after, which is the viscous kinetic energy term, is equal to our correction factor times the inviscid kinetic energy term. There should be an m dot here, so this should be alpha m dot U squared over 2. Okay, and then so our problem suddenly becomes a bit more simple, and what we have to do is just work out what alpha is. And we can see some limiting cases. Well, we can see one limiting case. If it was a uniform flow, then alpha would be 1. If it's a laminar flow, and we're going to deal with what a laminar flow is in a couple of lectures, alpha is going to be 2. And if it's turbulent, alpha is somewhere between 1 and 2. So when it's a little bit turbulent, it's a bit less than 2. When it's very, very turbulent, it's a little bit bigger than 1. Okay, so alpha generally is a function of the Reynolds number. Okay, so once we've got that, we've got a simple equation that we can start to use. So our steady mechanical energy equation now looks a bit like this. So what I've done here is I've divided everything by the mass flow, and I've got my various energy terms. I've got my internal energy, my pressure, my potential energy, my kinetic energy on the outlet, my kinetic energy on the inlet. Okay, so it's still a viscous flow here, and we haven't made any other assumptions other than it's steady and we've got 2 ports. So it's still pretty general. So now what we do is we say, well, we're interested in the mechanical characteristics of this flow, and we're not technically we're not interested in the temperature terms, but it turns out that these temperature terms are actually quite important, and these are the causes of all our viscous pressure drops. So we rearrange this equation to say, well, we're never going to have a thermal heat transfer through the pipe wall. We're not really interested in that. So this is effectively our pump, and this is the kinetic energy going out of my pump, say, and this is the kinetic energy, the total energy coming into my pump, and these are effectively my losses. So these are viscous losses. So you know, if you rub your hands together, they get warm. So it's effectively what you're doing is you're turning motion into heat, and that's an irreversible entropy generating process. And the same thing happens in a fluid. So viscous flows are dissipating energy because they're viscous. You're kind of rubbing one fluid layer against another, and this term effectively generates your losses. So if you did some careful measurements, you would measure that the outlet of a turbulent pipe is warmer than an inlet of a turbulent pipe. But these temperature changes are very small, and where they also generate pressure changes in an incompressible fluid, and it's these pressure changes that we're actually interested in. Okay, so we don't deal with these terms directly. We have empirical models for them. We're going to discuss these next. So what we say is that these viscous losses, which are kind of entropy generated, they generate entropy and they're sort of irreversible losses. These are characterized by empirical fudge factors, if you like, and we have 2 of them. So we've got this term, the F L over D U squared over 2. So this F, this is like a friction coefficient. This is like this is a bit like a drag coefficient for an object, and we have to do calculations to work out what this is for a pipe, and this kind of gives us pressure drop per unit length in the pipe due to viscous effects. And then we have this term, so we have n of these, so these are down to fittings. So if you have a bend in your pipe, or if you have a connection, or if you have a contraction or an expansion, each of these unit operations lose you some energy. They give you a loss, they give you a pressure rise. So these K factors are things that you look up in a book, and these will tell you what your loss factor is for that particular piece of kit. Okay, so these K and F are my empirical fudge factors for this effect, and these are scaled on the local kinetic energy. Okay, so this gives me my final form of the extended Bernoulli equation, which is, this is my pump term, this is my total pressure going out, this is my total energy going out, this is my total energy going in, this is my frictional loss due to my pipe wall, and this is my fitting loss due to what kind of fittings I've got along my pipe network. So when we start looking at the frictional loss in a pipe, we find that it's quite complicated, and it depends on two factors. It depends on whether the pipe flow is laminar or turbulent. So if it's laminar flow, so this ln/Cf, this is log of f effectively, and this relationship holds for laminar flow. And in a couple of lectures we are going to derive this, and I'll show you where this comes from. And then in a turbulent flow, it depends on whether the wall is rough or smooth. And if it's a very, very rough pipe, internal surface of the pipe, the pressure drop doesn't actually depend on the Reynolds number of the pipe. It's always the same. If it's a smooth pipe, so it's not very rough, then the pressure drop depends on the Reynolds number. Okay, so we're going to talk a lot more about this in a couple of lectures' time when we start talking about turbulent boundary layers and laminar boundary layers a little bit more. Okay, but this is your frictional factor that we use in the steady mechanical energy equation. Okay, so this is how do you get to the Bernoulli equation? So this is our mechanical energy equation. Some people call it the extended Bernoulli equation. Then if we say if there's no pumps, so with no work transfers, so this term goes to 0, and then we say that there are no viscous losses, it means that these two terms disappear, because there's no viscous losses, so F and K are always 0. And then we say it's a uniform flow, so these alphas go to 1. We then recover this equation, which tells you that which recovers the Bernoulli equation. Okay, so you can go from the steady flow energy equation to the mechanical energy equation to the Bernoulli equation, but you can't start from this and then start adding viscosity in these terms, because you're not starting from you can't just add viscosity, really. It doesn't really go that way around. So but some textbooks do this, so I don't think personally it's correct. Okay, so we've looked at the steady mechanical energy equation. It's a simplified steady flow energy equation with 2 ports. It defines a kinetic energy correction factor to get around our problem with defining kinetic energy at pipe inlets and exits. And we've introduced some fittings and pipe friction correction factors to deal with the viscous losses. And you can use this as this is a very standard engineering toolbox to calculate pressure drops in pipe networks. Okay, thank you very much.